Today I want to talk about how the proton's g-factor equals the electrons. If you've ever studied particle theory, then you know that g-factor is related to magnetic moment. And for the electron magnetic moment, the magnetic moment mu equals g, the g-factor, times E h bar over 4 times the mass of the electron, me. Now you see it sometimes written E over 2me times I, where I is the angular momentum, which is equal to h bar over 2. So it comes out the same way. And when you set it up this way, the g-factor is a little more than 2. 2.0023, etc. And this is considered one of the greatest successes in quantum field theory, that they've been able to estimate the g-factor to a high degree of error. And after doing a whole lot of fudging, although the first two terms, 2 is and an alpha term, are pretty simple. So we have this as, like I said, one of the greatest achievements of quantum field theory, supposedly. I'll talk more about that in another video, that it's not really as great as it's cracked up to be. So now, if we look at proton, use the same equation, the g-factor for the proton times E h bar over 4 m sub p, the mass of the proton, then you get GP equals 2.7928, etc. Now, when this is set up in some equations, they remove a factor of 2, divide by 2 times the mass of the proton, and then they say the g-factor is 5.85, etc. So double this. So, but that's just a factor of 2 shift, and it just depends on how you want to run the equation and where you want to put the g-factor. You also see that a g-factor for the electron written as negative, but in reality the negative goes with the electric charge, not the g-factor. So I consider the g-factor to be independent of the change in electric charge. Now, in order to simplify the equation and get it right, because when you calculate magnetic moment, you need a radius, you need a charge, and you need an angular velocity. That's how you calculate angular momentum. You don't calculate it with a mass. So in order to put it in the correct terms, you can look at the proton Compton wavelength, lambda p, the Compton wavelength, equals h over the mass of proton times c. And note this is h, not h bar. And if you rearrange and substitute for the mass of the proton, the magnetic moment becomes the Compton wavelength times the electric charge E times c, the speed of light, divided by 8 pi. And since the proton Compton wavelength is effectively the diameter, you can change it to a radius, and then you have a radius times E c divided by 4 pi. And the 4 pi term gives you your angular velocity, where c is a linear velocity, and you have to divide by 2 pi to get an angular velocity. But what that means is you're assuming a radius of 0.6607. Now you'll see in the textbooks they'll say, oh, the reason that the g-factor for the proton is so much higher is because it's not an elementary particle, it's a composite particle, so it turned out different because something in the internal structure is different. No. The reason it's 2.79 instead of 2.00 is because they're using the wrong radius. Because by using the mass of the proton, they're assuming a radius of 0.6607 when the charge radius measurements are higher. And I'll put up the groupings, but there's basically been 3 groupings of charge radius where I have group A is 0.916 to 0.912, and these are all fairly recent, in the past decade or so. And then the second group averages around 0.877, and the third group averages from 0.831 to 0.8409, or 0.8414 is another estimate. Well, if you plug these radii in instead of this radius, you get G factors of 2.014, 2.104, and 2.194, which are much closer to 2.002. In fact, you can see that when you get up to 0.916, you're getting really close to having a G factor that equals the electron's G factor. So what we can do is set the proton G factor equal to the electron's G factor, and then we have a radius of 0.921555 and change, which is just slightly larger than the 0.916 and 0.912 range. And note that these are still average results. They're still an RMS mean around a statistical average. So they're not limited by the speed of light. This is an absolute radius limit limited by the speed of light, so it can't be exceeded. So any sort of average measurement, a real physical measurement, is going to be slightly smaller, even if what you're measuring is the outer radius. So the fact that they measured 0.916 and a true outer radius is probably 0.921, that's actually pretty close. Now, I just did a video on solving this charge radius puzzle. Why are there 3 different groups of charge radii? And the reason is that everyone basically agrees that this charge radius structure that you're scattering against is likely made of quantum fluctuations. Well, quantum fluctuations have a wavelength and a frequency, and the wavelength varies sinusoidally with time. It expands and contracts. At the same time it expands and contracts, it rotates 180 degrees. So you get this sinusoidal curve that it follows. Well, if you measure the mean, the point where it's at its point either at the beginning or end, you get one measurement. If it's at its maximum, you get a second measurement. And then with the sinusoidal curve, you can get a root mean square measurement that's in between. That's typically used in measuring things like alternating current voltages. And so you can get a RMS reading. And it turns out that the outer radius aligns with 0.921. The RMS radius is about 0.88, and the mean radius is around 0.84. So if you have different experiments which just happen to measure the radii in different ways, that explains the charge radius puzzle. Then, looking back at the electron, if you substitute in the electron Compton wavelength, you find out that that also works. But you actually get the correct radius. You don't have to fudge it to get the real radius like we do with the proton. And this also turns out that with the electron, because the Compton radius works out as a real radius, which once again would have to be a structure made of quantum fluctuations, that's where the quantum fluctuations are rotating. And to be clear, the quantum fluctuations rotate individually, but it makes this whole structure look like it's rotating. So the whole structure isn't really rotating. It just looks like it is because the individual quantum fluctuations are rotating. The quantum fluctuations themselves may not be moving. So that leads to another problem that I mentioned in a couple other videos I'll link to below, that the spin is different. because the angular momentum is different. In the case of the electron, the angular momentum does work out to h bar over 2, as was put in here. But in the proton magnetic moment, the angular momentum is 0.697. So the angular momentum is different if you have this larger radius. So that's a problem where if you're assuming that the angular momentum is the same for all the particles, then that assumption's false. The proton, neutron, electron have all different angular momentum. So you can't just you can't just add up 1/2 plus 1/2 equals 1/2 plus 1/2 when you do some sort of particle interaction. And that totally screws up the way people introduce neutrinos to try to equalize the angular momentum, the spin angular momentum of particles. But anyway, it's very clear when you look at what the real radius is versus what the pretend radius is that has been used historically. We really need to be using the real radius, and the real radius gives us the real angular momentum and the real magnetic moment, wherein the g factor of the two particles is equal. And if the g factor of the two particles is equal, that can mean that the proton is elementary and that it does have the same physical structure as the electron. And so that's the assumption I work with when I'm working on my electron and proton models, that in the past people just screwed up when they came up with this different g factor. Well, I hope you enjoy this video, and if you do, please like it, share it with your physicist friends, and subscribe for my next videos. I'm sure I'll talk about this more. And then I have books for sale. In my particle theory book, Goodbye Quarks, the Onium Theory, I talk about basic particle theory of the electron and proton first, and then the onium theory in detail. I'll also link a paper below that I just published that has this information in more detail. And then I also have my quantum field theory books for sale. And I'm a retired independent researcher, so if you buy one of my books, that helps me in my retirement, so I appreciate that. And I hope you learned something new about quantum field theory or particle theory. So thanks for watching.